Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. This episode is brought to you by the Humid Climate Conference. Back in 2015, the Austin chapter of Passive House Alliance US was thinking about how to get more attention to the FIAS Plus 2015 standard in humid climates. And so the thought emerged, what if we put on a conference? I'm proud to tell you that this is an unmissable conference. It's a unique gathering of the best building science minds who are ready to talk seriously about passive house and humid climates. This event is entirely volunteer organized, supported by Passive House Institute US, and sponsored by some of the best product manufacturers and industry consultants in the country. And it's sold out in its first try. But it's happening again this year, May 21st and 22nd, with a great speaker lineup. We're talking Joe Stiebrick, Lou Harriman, Richard Corsi, Matthew Tanteri, and the list literally goes on and on and on. Find out more at humidclimateconference.org. Early bird tickets are limited and they're selling quickly, so don't miss out and be left wondering. Register today. That's humidclimateconference.org for tickets. Now sit back, relax, and enjoy the episode. Hey listeners, just a housekeeping note on this episode. You'll hear mention of someone named Greg, who you actually won't hear on the episode. Originally, the interview was a 3-person interview between Kristof, Graeme, who you'll hear, and a fellow named Greg. He had to leave midway through the episode. We lost all his audio, so we edited accordingly, but there are a few points that we just couldn't get out mentions of Greg. Don't worry, Greg comes back in part 2 of this series on architectural yogurt. Hope you enjoy.
Welcome to this.
Welcome to the
Building Science
podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to architecture and design.
Brought to you by Positive Energy in Austin, Texas.
Hello and welcome back, everybody. Welcome back to the Building Science Podcast. I'm Kristof Irwin here with my trusty sidekick, Miguel, as always. Today, we are going to be talking about biofilms and probiotics. You just wait. This is cool. New home smell or new car smell. Everyone knows that it exists, but very few people know what it is. And what it is smell. So what's smell? Well, smell is a molecule of a substance that was in the air around you that went into your nose and clicked into your olfactory system, which is basically a protrusion of your brain, which is kind of wild. So basically, this molecule of something clicked into your brain, generated a signal we associate with a smell. So when you smell a rose, right, a piece of rose is in your nose. When you smell, like my house, I have dogs. Probably smell dog smell. Cooking odors, if you know that babies live in a house because you can smell dirty diapers, just think about that. And really what I want to get to, though, is this idea that, I don't know if you've noticed it, but when you go over your friend's house, it smells different than your house, right? And what is going on there? And what's going on there is that the cooking, the people, the surface chemistry all around you is emitting particles and gases into the air. That means it's emitting molecules into the air that you can receive as an odor. So that's my kind of obtuse introduction to biofilms. What I'm talking about here is the indoor surfaces are emitting surfaces. They're rich with chemistry and biology, and this is a subject that doesn't get enough attention, and that brings up biofilms. So first, before we talk about that, let's talk about who's with us today. Today we have Graeme Marsh. He's the managing director at Z Bioscience Incorporated. Graeme, tell us a little bit about yourself and Z Bioscience.
My background is that I was, believe it or not, in investment banking for over 20 years on international assignments. And then back in the late 90s, I set up a consulting group that specialized in dealing with small startups, mainly in the area of technology. And that technology was not so much IT, but more related to chemistry, pharmaceuticals, and healthcare. And I came across Z Bioscience around about 7 years ago and realized that their approach was probably the most disruptive technology I had seen in terms of its potential to impact everybody across the entire spectrum, which was the use of biology in the form of probiotics to address the presence of biofilm as opposed to the pure chemistry approach. And so I've been with them for 7 years and been an enormously fun ride. I met up with Greg around about 6 years ago when we realized we had a solution for HVAC in terms of thermal transfer improvement and also the eradication of odors such as dirty sock. And so Greg and I have been working together since then.
That's awesome. I'm going to try hard to push that topic because we're definitely going to get to HVAC. And probiotics generally, for you guys listening, if you haven't been keeping track of probiotics, now is the time to start. It's basically revolutionizing how societies deal with cleaning. Instead of detergents and antibiotics, basically, we have this new approach. Tell us what a biofilm is.
Biofilm is a collection of microbial communities that are enclosed by a matrix of extracellular polymeric substance, also known as EPS. This is think of it like a form of saran wrap. Bacteria are generally free-floating in the air. They arrive, they land on the surface, particularly pathogen bacteria, like to attach. And so they excrete this EPS, and it basically protects them. It's a separated open channel network of plastic, for want of other terms. Wow. And they build this over the top of themselves, and as more free-floating bacteria arrive on the surface, and bear in mind that we're surrounded by about 100 trillion bacteria free-floating in the air every day. All these friends. Trillion. Yes, it's huge. I mean, we have no idea what's going on. We're only just because of the advances of modern science starting to really come and appreciate this. You'll have what you think is a clean surface. Bacteria basically settle on it. The first thing they want to do is attach. They excrete this EPS, or extracellular polymeric substance, which is like a saran wrap over the top. And that protects them. It allows them to then replicate. And more bacteria arrive on the top. And it slowly builds up at this very microscopic level. You can't see it. Most people tend to feel that biofilm has to be wet and slimy. That's not accurate. The vast majority of biofilm is a dry biofilm, and it's on virtually every surface. And by the way, in terms of healthcare, it's biofilm that is effectively making the disinfectants and the sanitizers and all these conventional cleaning technologies ineffective.
Yeah.
Because as the CDC and the National Institutes of Health have pointed out after many years of research, that biofilm is preventing those chemistry-based cleaning agents to actually penetrating and trying to get to the bacteria.
That is awesome. All right. So going back a little bit, so extracellular polymeric substance. I mean, I like polymeric. I get that part because it's a mer is like a chemical, little molecule, and then poly means many. So a film is like a polymeric sheet. But when you say extracellular, what do you mean by that? It's just outside the cell, or what does that mean, extracellular?
Okay, so here's how it's produced. Effectively, when bacteria arrive and attach on a surface, first thing they need to do is eat. It's a bit like if you've got teenage kids and they come home from school with their friends. The first thing they do is go to the refrigerator, and I'm going off to Costco or Sam's Club. As a result, when they eat, what they do is these pathogen bacteria excrete the EPS.
I see.
The biofilm. So it's a byproduct of their functionality of being present. They eat and they excrete the EPS.
Good enough.
And that is their own protective substance.
Perfect. And then the very beginning of your definition, you said microbial communities. Could one of you talk a little bit more about what you mean by a microbial community? Like who might be a resident of that community?
The biofilm that are produced that are of concern to us generally are produced by pathogen bacteria. So examples of that would be Legionella, E. coli, Mycobacterium, strep, salmonella, staph, MRSA, pseudomonas, just to name a few of the ones that we're all too familiar with.
Any friendly?
And
are there any friendly microbial communities?
Well, now we're getting down to a rather interesting and deep level of science. There are two effective influencing communities of bacteria. You have your pathogen bacteria and you have your beneficial bacteria.
And pathogen implies that it's not good for human beings somehow. Is that right?
A pathogen is generally regarded as a gram-negative, not always, but mostly, and it is regarded as potentially a harbinger for unwanted contamination that could threaten human health. There are beneficial communities, and probiotic bacteria are a major portion of the beneficial bacteria.
Awesome.
And so this is where we get down to a little bit of a deep science. The biofilm that the pathogens excrete when they arrive on a surface is one that is effectively designed to attach and protect. It's also important to know that pathogen bacteria replicate very quickly. Some as quickly as every 5 minutes, all the way through to some that replicate, over a period of 12, 15 hours.
Interesting.
Now, to give you a bit of an example here, sort of E. coli and salmonella can replicate very quickly. Clostridium can replicate every 10 minutes. E. coli every 20.
Wow.
So when you start to understand that, you see how quickly they build.
Up or
now,
out?
On the other side of the spectrum, you've got your beneficial bacteria like probiotics. Well, there's two core differences here to understand. The biofilm that is excreted by the beneficial bacteria doesn't attach like the biofilm does of a pathogen community. It tends to be more free-floating and is able to sort of almost hover across the surface. But what's really interesting to note here is that beneficial bacteria can replicate, they replicate at a much slower rate. So some probiotics might only replicate every 2 to 3 days. So when you start to do the math, what you can see here is that you've got a rapidly replicating community of potentially harmful bacteria in the form of pathogens who generate a protective coating in the form of the biofilm that is attached to a surface. On the other side, you have the beneficial bacteria that replicate much slower, and the nature of the biofilm that they produce is basically very different in the sense it doesn't have the same extent of attachment qualities to a surface. Now, there's one other core difference, if I could just make this point. The reason probiotics are really helpful in addressing the presence of pathogen biofilm is that when the probiotics eat, what they mainly excrete is known as a biosurfactant. This is nature's little cleaner. The biosurfactant that they produce does comprise, as one of its constituents, enzyme, but it's always surrounded in a natural liquid with some other components, and it has the ability to break down the biofilm generated by pathogen bacteria.
Wow. And what do they
And when it breaks that down, that pathogen biofilm, what it does is it releases additional food source.
So they're eating the harmful bacteria and excreting an enzyme that helps them eat more of it.
Well, they're actually eating the food source and breaking the biofilm down to release additional food source. They're not actually eating the pathogens. So when we use probiotic cleaners, what we're doing is utilizing the scientific principle known as competitive exclusion. Now, competitive exclusion basically says where you have two species competing for an existing resource, aka the food, what happens is that one will survive and the other will basically starve. It will be forced off or out of the environment because of the lack of access to food. So probiotic bacteria-based cleaners are putting an overabundance of beneficial bacteria onto a surface such that they so dramatically outconsume the food source that the pathogens effectively starve to death. There is no neurotoxic killing of them. The environment, through the presence of the probiotic bacteria, is made hostile to the pathogen bacteria, and they just can't exist in it. Nothing has been able to mutate or adjust to basically survive starvation. And if I go back to the example of my teenage kids coming in, yeah, if my fridge doesn't have food, it's the place next door.
Mm-hmm.
They just move on. So it's that sort of environment. And as long as the probiotics are on that surface in such an abundance, the surface cannot be rehabitated or recolonized by the unwanted pathogens. So the probiotics are providing a very safe means of addressing the presence of the pathogens, A, by not creating any risk of mutation, because nothing's been able to mutate to survive the absence of food. It actually breaks down the very biofilm that effectively the chemical agents of disinfectants and sanitizers and other cleaning chemistry agents have not been able to penetrate and therefore have been proved ineffective. The increasing levels of hospital-acquired infection, despite ever-increasing strengths in chemistry, are an example. The probiotics have the capacity to migrate across the surface in search of the food. So if you miss something in a wet wipe, for instance, or a wet mop application, if there's a joining food source there and their probiotics have eaten the food source here where they were first applied, they'll move across the surface chasing it down, just like your kids will go next door when you run out of food. Their presence, it makes the surface hostile or inhospitable to the potential rehabilitation and recolonization by the pathogens. So they provide this ongoing protection. And that's where they're fairly unique.
That is so awesome. I mean, it's unfortunately, it's wrappered in a lot of fancy terms, but it's basically a revolution in the way we approach making a surface clean and germ-free or pathogen-free. It's so exciting.
One of the terms, if I could just, here's a way to sort of think about it. Instead of an actual fact cleaning through killing, probiotic-based cleaning is a means of bioengineering a surface such that it's hostile to the unwanted pathogenic bacteria and promotes a much healthier and supportive bacterial ecosystem on the surfaces of any indoor environment or on heat exchange equipment or HVAC or whatever. I think what's very important is to understand how the biofilm forms on a coil. In a lab, if you're wanting to make a biofilm, you'll take a supposedly clean surface and you just drip water on it. And just doing that is known as creating a biofilm generator. And that biofilm, that dripping is what is effectively happening in a coil. As the air is flowing through the coil, it's there to actually strip the moisture out of the air. And it collects on the fins and it collects on the actual coil tubing itself and on the different parts of the actual air handling unit as the air is flowing through. And so you end up creating this biofilm on the fins and on the coil. And biofilm is the biggest impediment to the thermal transfer efficiency of a heat exchange surface. So that in some research that was done in association with the California Society of Healthcare Engineering, a biofilm of 150 microns.
About as thick as a hair.
Now, 100 microns is about the thickness of a human hair. That can increase the energy consumption required for that unit on an HVAC, on a heat exchange unit to have to be 5.3% greater to achieve what's needed. When you get to 900 microns, they estimated that it was between a 30 and 35% increase in energy consumption.
And what is the typical thickness? Is 900 like ridiculously thick?
Not necessarily. It depends. I mean, Greg is actually about to go and deal with a unit in the next couple of weeks where the maintenance on it has been so poor that I think 900 microns would probably be a conservative estimate as to the thickness of the biofilm on that unit.
That's fascinating. This 30 to 35%, that's a combination of impediments or reduction in both heat transfer and mass flow or airflow across the coil, right? And okay, I wanted to actually jump back. I know the mammalian aspect of us, our immune system, our behavioral responses, part of it is to protect us from being exposed to pathogens, right? So if something smells bad or putrid, we're not going to eat it. But I also know that there's odorless things in the air that are bad for us. I guess what I'm getting to, do either of you know if there's a link between something smelling bad to us and them being pathogenic? Is there a correlation there?
Well, that's a good question. On the whole, offensive odor is nature's method of indicating that something's not right. So, for instance, you take something like E. coli or salmonella, right? You can pick up a piece of food, and if it's not right, it smells. It's nature's warning sign that something's not right, but it's not always present. You take something like Mycobacterium tuberculosis, which is in water systems, and even Legionella. You don't smell it, but it's also quite harmful.
Fascinating. Okay, good enough. Let's get back to biofilms. Well, before we get to biofilms specifically on HVAC, you talked about how quickly they build. You talked about replication and spread. And we talked about just now, it's this thickness. It can go from 150 microns thick to 900 microns thick. It's also spreading sideways, right? So they're building both up and out at the same time. Is that right?
Yes. And well, it's always dependent upon the environment. Spread of biofilm is often related to the environment in which it's occurring, levels of maintenance or lack thereof, and particularly in HVAC systems. But I'll give you a bit of an example that I think most people can relate to. How often do we see some mold in a corner? Right? It's very isolated. You can visually see it. And what happens is in that tight corner is usually an accumulation of moisture. The airflow coming through it is maybe not great, so it's not aerating properly. It's probably on a surface that may in actual fact have been compromised, so it's been able to actually get into some of the drywall or into the grout. And it's probably in an area that's not regularly cleaned. So when you take those considerations, they can contribute to it actually being very prolific in that little corner, but it doesn't necessarily grow right across the entire area. However, we've also seen instances where you can tell it started in a particular place, but because the overall environment was such and it wasn't being properly maintained and for what other potential reasons, it has managed to spread over a much bigger area. So it's very situation specific in terms of the capacity for it to spread.
Fascinating. Let's just take an HVAC coil for an example now. And typical HVAC coil, there's A coils and slab coils, but residential ones, they'll be 24 by 30 inches. So let's say 2 feet by 3 feet. That's 6 square feet. And is it the case that the biofilm? Oh, by the way, that's 6 square feet of just face area. The surface area is immense, right? Because we have all those fins. Are biofilms going to be coating?
Yes.
Every bit of every surface on the heat exchange surfaces and on the tubing, or do they have paths that they stick to, or do you know? Is it
again very environmentally specific and also down to how well it's maintained? But let me give you an example. So take somewhere like Albuquerque, New Mexico. It's a bit like Denver. It's a mile-high city almost. It's very dry, low levels of moisture in the environment. And so not a lot of moisture is being stripped out of the air when it's an actual fact, like in a cooling system mode. However, if I go out to Hawaii and I take exactly the same unit where humidity levels are much higher, there's high levels of rainfall on a regular basis, And the temperature range tends to be not dissimilar at times to most of the year to Albuquerque, but it's a different environment. Then, yes, the risk of biofilm forming on the coils in Hawaii are dramatically higher than they would be in, say, Albuquerque.
Because of the moisture presence.
That's right, because, as I said, the way you make a biofilm generator in a lab is you take a surface and you drip water on it. And so in the cooling cycle, for instance, for HVAC, what you're doing is you're cooling the air and stripping the moisture out of the air as it passes through the unit. And that moisture accumulates on the fins, the coil, and the interior aspects of the air handling unit before the air goes down the duct. So, yes, that is a primary consideration.
Oh, yeah. Even if you're in a dry climate, the humans and human activity in a building, in a home, are generating moisture.
Well, now here's what's also important. Biofilm forms on a surface before you'll actually get mineral deposits, be it on the interior aspects of a premise water system pipe, for instance, or on the exterior surfaces of the fins and the coils and interior components of an HVAC an air handling unit. What happens is that it's the biofilm that forms that effectively allows the mineral deposits to accumulate on the surface, because by nature it tends to be a little sticky. It has an adhesive quality, varying in multiple degrees, again, depending on the environment. But it's those mineral deposits that are potentially in the air or in the water system through that the biofilm forms first, then it accumulates, then it becomes a means by which the mineral deposits can accumulate. And then, of course, as you continue to have moisture pass over it, like in a pipe, or you continue to strip moisture out of the air on an HVAC system, then more biofilm forms over the top, and you get this layering effect going on a constant
and how do
basis.
you see it or measure it?
There is a very interesting question.
Okay.
It's a challenge, because it's often to get an accurate measurement and understanding. You usually do some form of laboratory-based plate count, and you'll basically do samples, and then you'll test for specific pathogens, and that'll give you, the population will give you an idea. If it's a dry biofilm, say, on a surface, such as what you'd see inside a hospital, where the biofilm is basically being formed and protecting pathogen bacteria like MRSA that can be a potential threat to the patients, the staff, and visitors. In a HVAC or system, you'll often see it. It's physical. It ends up being a slime in the drain pans. It can be clogging the P trap. It can, be physically seen on the fins. And where you've got this often accumulation of organic material that's basically blocking the airflow, you can nearly bet your bottom dollar that there's going to be a significant level of biofilm there that has helped that organic material to accumulate on the surface.
Or something. It's an early adopter.
So when you look at an internal dynamics of a pipe, what you look at there, Kristof, is a ongoing accumulation. As the internal diameter shrinks, you can physically see it. And you look at it and you go, oh, wow, there's a lot of mineral scale there. But really, it's layers of biofilm, mineral scale, biofilm, mineral scale, biofilm, mineral scale, and it just continues to build up. So when we start to deal with HVAC issues such as Legionella, Mycobacterium, it's increasingly being understood that the core source of the issue is the presence of biofilm. You could give me a couple of seconds here. I'd like to reference a couple of really good scientists in this area. One of them is Professor Nicholas Ashbolt, who was for 7 years the head of waterborne pathogen research for the EPA out of their facility in Cincinnati. He's a fellow Australian. Don't hold that against him. But he left that position about 3 years ago and has now got the chair of public health over at University of Alberta. The other person is Professor Joe Falkenham from Virginia Tech. Again, a leading expert in this in the area of waterborne pathogens. And I've had the pleasure of speaking with and working with both of them. Nick developed a theory some years ago, which has been increasingly supported by additional research, that Legionella in HVAC systems is part of a cycle. There's the presence of the biofilm, or the presence of bacteria in the water system who establish a biofilm on the surface, and that biofilm ends up protecting the pathogens that make it, of which Legionella is one particular species of pathogens. And they continue to build this up. In the meantime, you have amoeba floating around in the water system, and the amoeba feed off the bacteria in the upper layers of a biofilm. Now, what happens is most of the Legionella bacteria are what they call parasitic, so that when they're consumed by the free-floating amoeba moving through the water system, once they're inside the amoeba, it actually gives them an opportunity to replicate at an accelerated rate. And they replicate within the amoeba to such an extent that they end up bursting it. The technical term is they lyse. So they basically burst the amoeba. But the amoeba is playing a very important role. The amoeba is basically a reproductive vector in the sense that it's allowing a rapid reproduction of the Legionella bacteria. It is also a transportation vector carrying the Legionella bacteria further down the water system. Whilst in the amoeba, they're protected from the methods of hyperchlorination and high temperature. So it's a protective vector. So this cycle starts with the formation of the biofilm and the presence of amoeba. And the amoeba are able to then, because of that, feed off the bacteria in the upper layers of the biofilm, allow them to reproduce, transport them further down, and protect them from potential conventional methodologies of addressing Legionella. So if we go back to New York City in 2015, where there was a substantial array of headlines in the second half of the year about outbreaks of Legionella in several major HVAC systems in New York City, it was then determined by New York City to adopt the ASHRAE standard, which had just been completed after 3 years, or was it 5 years, to treat Legionella on all the cooling towers. And they did. And it cost facility managers a lot of money, and it cost the city government a lot of money. And they did that. But within 4 to 6 months, nearly every one of those cooling towers that had been treated with the hyperchlorination and high temperature basically were showing positive again for the presence of Legionella. Not necessarily at a state that was actually dangerous, but the reason comes down to they had not addressed the biofilm. And this is the final part of this equation. And I'm sorry for taking so long, but when you use hyperchlorination, what it does is it does not get rid of the biofilm. It actually is being now shown that what happens is that hyperchlorination causes the upper levels of the biofilm to harden. And in doing that, it makes it even harder for the hyperchlorination to basically penetrate the biofilm and get to the bacteria, and becomes actually a further protective layer. And it also protects it from using of the high temperatures. So in a well-mature premise biofilm, or biofilm in a premise water system, or in a cooling tower, it's not necessarily getting rid of it. And that's exactly what the example in New York City showed. So very often, a lot of the standards that we have been generated by people with lots of expertise and experience, but it's based on what they have done. And it's not necessarily a forward-looking, it's more a rear-looking based standard. And so we're starting to now come to understand that because of the work of people like Joe Falkenham and Nick Ashbolt, that we have been using chemistry to address what really is a biological problem. And we know from the healthcare industry and from the research by the CDC and the National Institutes of Health that biofilm prevents the disinfectants and sanitizers like Quartz, bleaches like the chlorine based products that they use in treating Legionella and water systems, it prevents them from actually getting to the bacteria.
Wild. Yeah. Oh, absolutely. Yeah. And I didn't realize how critical it was when I set up this interview. I mean, it just shows how important it is to get out of the office and go to conferences. I mean, I saw Greg speak at IAQA, and that led to this. Let's talk for a minute. And by the way, we're getting close to the time we need to start winding down, about cleaning in general, right? Because we were talking a little before the show, the old ways of cleaning, which are still happening, were detergents and disinfectants. And it seems to be probiotics is emerging as a new way. Could you kind of briefly describe detergents, disinfectants, and how probiotics cleansers relate to them? Or
Yes, I'll try and be brief. Let me put this in a historic context.
Mm-hmm.
Back from the days of Babylon, our cleaning approach to cleaning has been to use some form of chemistry, and there it was a form of ash and water with some form of physical activity. So a combination of physics and chemistry. And really that hasn't changed since the time of Babylon. It's just that we've got way more complex and stronger and toxic chemistry, like 6th generation quaternary ammoniums. And as a result, what's happened is that for 2,500 plus years, we've been doing the same thing. The importance thing to understand is, again, as Nick Ashbold and Joe Faulkner have explained to me, microbiology 101 is very simple. No matter how aggressive the chemistry, the bacteria will ultimately adapt. So let me take you now to an example of, say, Lysol. Which I think most people can associate with. And you pick up a can of Lysol and it says, we kill 99.99% of the bugs. Well, I have 2 points to make on this. The first is, what about the 0.01% that it doesn't get, right? They are the basis of the survivors that over time can become stronger, which when you consider it, we're now on to 6th generation quaternary ammoniums, and we still have high levels of hospital-acquired infections in areas where they really do focus on cleaning very aggressively. Just last night, there was a report out of the university from Newcastle upon Tyne in the UK, as reported in the UK's Telegraph, about how your antibacterial wipes, your Lysol wipes and your Lysol sprays, and I'm just using Lysol because it's a generic name in the minds of most people, are ineffective. Within 20 minutes, the bacteria are back. And that it's also been reports that have come out over the last several months with regard to healthcare workers, nurses, and environmental services personnel working in hospitals where they're constantly using quaternary ammoniums like a Lysol disinfectant cleaner. Because of they're inhaling it, they have a significantly higher rate of CPOD, I think it's the right term, in terms of respiratory disease, as an example. And then just last week, another study came out indicating that people that are using these sorts of chemistry cleaners in the home are effectively got higher levels of respiratory disease, and it's almost they equated it to the equivalent of smoking 20 cigarettes a day. That study was more sensational in its headline than it was, I think, probably in its substance. When it comes to cleaning, the primary reason that the core basis of cleaning has always been, you clean, you rinse, and you disinfect. And the idea is that disinfectants make lousy cleaners, cleaners make lousy disinfectants. They're sort of some of the age-old ideas that have been around. What's happened is, because of time resources, we've tried to combine the cleaning and the disinfection in one process, and so now we've got something that's pretty ineffective at both. What's interesting is, and when you go to your green cleaners, it's really your not-so-good cleaners from a health perspective that have been diluted to the point that they can be regarded as safe, but then they don't actually clean. Soil removal is very low. And it's interesting. I mean, I was talking to a county office of education with a gentleman who has a couple of degrees from universities. He was highly intelligent. a lot of experience in janitorial services in terms of maintenance of schools and with a focus on maintaining hygiene and health to maximize average daily attendance rates from a revenue perspective. And he said, okay, so I see all these green cleaners and they're great. They're green, but they don't clean. And this is a common thing that I've heard over the last 7 years. Why do we disinfect? This is a really interesting question. The reason we disinfect is because our cleaners aren't really working at getting rid of the biological contamination. We've been really good with the chemistry and the physics at removing soils, generally speaking.
Yeah.
But we've not been very good at addressing biological contamination. And the biological contamination is now critical. The United Kingdom set up a special commission which estimated, it was released on almost at the very end of 2014, so it's really effective from 2015. In that report, after several years of study, they determined that by 2050, more people around the world will probably die from infection than they will from cancer. And that's a very significant factor, and it's driven by this concept of antibiotic resistance, which means that since 1940, we've not really paid a lot of attention to cleaning, because if I get strep throat or, an infection from my environment, I go to the doctor and I get an antibiotic. But we're now at a point where antibiotics are working less and less. The very early stages of it, but it's likely to be, a logarithmic progression. The whole idea of becoming more careful about use of antibiotics is there. What this has brought about is that cleaning, for the first time since before the introduction of antibiotics in the 1940s, is now back to being the front line in the defense of public health. Yeah, so if we take the fact that some of the cleaning chemistries and protocols and approaches that we've had are not working, hospital-acquired infection rates being a prime and probably the most measurable example. Combine that with the fact that we can't quite get antibiotics to work as well as they have, and that the level of adaptation to developing resistance to antibiotics as acted by the pathogen seems to be increasing. We're back to needing to clean more effectively. Einstein once said that the definition of insanity is doing the same thing again and again and hoping to achieve a different result. Well, all we've done is increase the chemistry strength, but we're still not getting an improvement in the result. The idea of the probiotic cleaners is to effectively introduce a third leg to the cleaning equation, taking physics and chemistry, but adding biology. So going back to what I said at the beginning of the program here, the introduction of a biological solution to address what is really a biological problem. And by definition, they have to be safe. For a probiotic cleaner to be able to successfully carry the probiotics, they have to be pH neutral. So it's safe for any moisture-tolerant surface. They have to have very safe chemistry, because if it's a toxic chemistry, it will actually kill the probiotics. So by definition, it becomes a very successful screen cleaner that introduces a third leg. And I've seen studies that have been done of, say, even our cleaners that indicate that we're in the top 5% of all cleaners tested in terms of soil removal. So it's a green cleaner that's doing something that the other green cleaners haven't been able to do. And that's partly because the probiotics are also active in terms of soil removal. So does that answer your question?
Every time you talk, I get more questions. So to summarize what you just said is 2,500 years later, we are due for an upgrade in how we approach the science of cleaning. In fact, our approach to cleaning has had some unwanted outcomes. I guess as a race of beings, we're in an era of being skillful with microbiology right now. I mean, gosh, I watched Jessica Green at a conference recently in Houston, and she has a TED Talk out. So the indoor microbiome.
She's a bit of a rock star.
This idea that you and I are human, we think of ourselves as human, but really we're bacterial symbiotes, and that our human microbiome is intimately related to the indoor microbiome, which is actually composed of biofilms and this rich ecosystem that we are and that we walk around in all the time. We're due to upgrade our understanding and how we deal with it. In fact, I think that's kind of like my wrap-up comment. Do you have any wrap-up comment that you'd like to leave people with? And I do want to point out before you go that I would like to make sure everybody knows that we're going to have in our show notes, we'll have a link to Z Biosciences. And specifically, since this is the Building Science podcast, we're going to be having a link to the cleaner that you're going to tell us about that is for cleaning HVAC coils. So final thoughts, please.
Well, you mentioned Jessica Green, and Jessica was a major inspiration for me. In her first TED Talk, she finished up by effectively saying, look, we have come to an appreciation of the need and importance of, sort of a safer, indoor microbiome or, bacterial ecosystem. And she said, so we take yogurt as a way of introducing healthy, beneficial bacteria to our gut to make us healthier and strengthen our immune system. And she's standing there. Behind her is a photo of a spoon with yogurt. And she says, so I'm looking for architectural yogurt. I'm looking for yogurt for a building because that's what we need to do. Probiotic cleaners are exactly what Professor Jessica Green asked for. We are that healthy biological yogurt that will improve the interior biological ecosystem of facilities where occupants spend 90% of their time, be it at home, be it at work, even in public transport.
Wow, Graeme, thank you so much. This has been very eye-opening for me, and I really appreciate your time and your expertise, and I wish you great success in all you're doing.
No, and thank you very much for the opportunity. I'm sad Greg had to disappear so quickly because Greg brings such an enormous array of experience. I mean, one of the great joys I've had is to be able to work with Greg. I mean, his 30 plus years experience in HVAC. You did ask the question about the product for HVAC. We've developed two specialty lines of product for HVAC. One is a probiotic coil cleaner known as AC-C. Biosurfactant coil cleaner. And we have an additional product called the AC-S, the S as in Sam, for our probiotic coil spray. We have used that coil spray post-cleaning through automated systems onto large commercial coils that have basically helped prevent the coil needing to be cleaned for over 3.5 years. And the only reason was that it had to be cleaned after that is somebody forgot to fill the bucket up. This was a system that delivered the AC-S protective coil spray into the coils through a manifold, a very simple manifold put at the front, 2 times a week for about 2 to 3 minutes at a time. And that continued to keep a high level of probiotic bacteria on the system that prevented it from basically developing the sort of biofilm buildup.
Did the probiotic cleaner that you put onto the coil make its way into the air and then make its way onto surfaces around the indoor space?
No. And this is a good question, and it's one we get asked a lot. And I wish Greg was here because, as Greg will tell you, there have been a number of studies about, how far can bacteria like that be thrown down a ducting system. The bottom line is no. It basically is arriving on the coils and it's there where the food source is. And as long as the food source is there, it continues to munch. By the way, everything in our products is being used and it's specifically designed for use around children, people with chemical sensitivity, and animals. And we've had a huge amount of experience over the whole 10 years of people basically inhaling it and not having any issues. And I mean, inhaling it several times a week over multiple years. And we've actually been regarded as a major component by fogging a product very similar to the protective coil spray into poultry facilities where they had outbreaks of respiratory-related diseases that they couldn't otherwise address.
The wow just goes on and gets bigger and bigger. Man, this is awesome. Okay, also your contact information, will you allow us to put that in the show notes in case people want to get to you and Greg as well?
Absolutely. Kristof, I'll send you two links, one to our website and one to a video link. That's a 3-minute video. It's an animated video that explains probiotics.
That's fascinating. All right. Thank you so much, Graeme. Sending you a huge thank you and a
No, well, look, thank you. I really appreciate the opportunity. It's been a great honour to be here, and I thank you very much, and I appreciate it, and happy to answer any questions that you have as a follow-up or that any of your audience might have.
Thank you, Graeme. And thank you all for listening, and talking to you next time. Bye-bye. All right, we're done. Graeme, that was awesome.